Hello and welcome to my channel, Boo Snakes and More. Today we're going to be talking about molecular science. So please like this video and subscribe to the channel. And for more videos like this, also watch my other house channel, Annie Snakes and Stuff. My youngest son's channel, He Needs Toys and Games, or my oldest son's channel, Little Chris 10. Now let's dive in. Advances in molecular chemistry led to the synthesis of hydromoleculate sandwich molecules, challenging to create but offering the potential for new chemical discoveries and industrial applications. Ander Schaefer and Agana Biskoff in the laboratory with a sample of their new diatomaceous credit Syracuse University.
I am a man and you are not
The first and the best known molecular is porcine, which contains a single iron atom. Sandwich complexes are now standard topics in inorganic chemistry textbooks, and the bonding and electric structure of metaclons are covered in undergraduate chemistry courses. These sandwich molecules are also significant in industry, where they serve as crystallists and are utilized in the creation of unique metamorphoses.
Show the camera.
Nobody knows
Or
exactly.
Maybe new family member. Our new family member.
We don't even know if it's our new family member. We don't even know if she's staying.
I don't care what Dad says.
Your dad pays the bills.
By what Dad already said, it's most likely staying.
And the bonding and electronic structure of molecules are covered
if it stays here,
in undergraduate chemistry courses.
It's going to be Lou.
These sandwich molecules
who talking on the damn phone
are also significant in industry, where they serve as crystallists and are utilized in the creation of unique metamorphoses. Nobody knows exactly how many sandwich molecules there are today, but the number is certainly in the thousands. And they all have one thing in common: a single metal atom located between two flat rings of carbon atoms. At least that was what was taught up until 2004, when a research group from the University of Swivel made a startling discovery. The Spanish research team succeeded in synchronizing a sandwich molecule that contained not one but two metal atoms. For a long time, this dimethyl containing two zinc atoms remained the only example of its kind until a group in the UK succeeded last year in synchronizing a very similar molecule that contained two selenium atoms. But now, Agana Biskoff, a doctoral student in Dr. Andre Schaefler's research team at Syracuse University, has taken things one big step further. She has managed to synchronize in the laboratory the world's first hydrometric sandwich complex, a diamond electrolyte that contains two different metal atoms. Shortly after the discovery of the first diametrolite in 2004, theoretical work indicated that diametrolites do not necessarily have to contain two identical metal atoms, and that a complex with two different metal atoms should also be stable. These predictions were made on the basis of quantum chemical modeling calculations using powerful computers. Despite this predicted stability, all attempts to create such a molecule in the lab were unsuccessful until Agana Biskoff's current breakthrough. It is really exciting and special when you realize what you're holding in your hands. To the naked eye, it just looks like another white powder. But I can still clearly remember the moment when we first saw the experimental determined molecules structure on the computer screen. And we knew that we had a sandwich molecule with two different metal atoms, said Dr. Andrew Schaefer. With carbon rings you choose is just as important as which metal atoms you want to enclose between them. This is critical because the electronic structures of the circular carbon rings and the metal atoms have to match one another, explained Igana Biskov. The metals contained in our hyperbarometric diatomaceous are lithium and aluminum. Calculations predicted that these two metals would be stable candidates because their electronic structure is in some senses similar to that of two zinc atoms, which we knew could form a stable diametralike. But what sounds so simple and straightforward took months to achieve. The molecule turns out to be so reactive that it can only be synchronized, stored, and analyzed under an inert nitrogen or on-again blanket. If it came into contact with air, it would simply decompose. Once it had been synchronized, the molecule needed to be characterized, which involved a whole team of scientists from Maryland University. The results of their work have now been publicized in the highly respected journal Natural Chemistry. A hypermetrobatic determinant represents that what is effectively a whole new class of sandwich molecules, said group leader Dr. Andrew Schaefer. Who knows, maybe it will also be included in a student textbook one day. But first of all, we need to study it further. At the moment, we have a pretty good understanding of its structure, but still know very little about its reactivity. If we find other suitable combinations of metal atoms, it may well prove possible in the future to synchronize other hydrobarometric tetraclones. The enormous significance of this class of molecules is underlined by an award of the Nobel Prize in 1973 to the German chemist Ernst Otto Fliescher and the British chemist Geoffrey Wilkinson for their pioneering work performed independently on the chemistry of the organometric so-called sandwich compounds. Reference: A lithium-aluminum hybridizers by Igor Alexander Bischoff, Sergey Dents, Philip Stern, and Bernard Mansigan. Thank you for watching this video, and peace out till the next one.